Okay, so here's what this looks like. The curved array produces basically two curves. There's one curve which corresponds to the face of the transducer, and then there's another curve which corresponds to the angle that the transducer swings in space. Now this is not a 2D array, this is a 1D array with a mechanical motion that produces the third dimension. This is very similar, this is exactly what's used in almost all the 3D scanners today. This still works for this technique, and this is claimed there's volume flow. But you got two curves. Now, what's interesting about this is you don't need a plane to integrate this flux. All you need is a continuous continuous surface. It can even be piecewise continuous. It doesn't have to be smooth. So this is very forgiving. And it turns out that the easiest surface to use is a curve, a section of a torus, or not a plane, but that's a detail in the technique. The technique works just fine with planes or curves. What you end up with then is a cross-section of the vessel which corresponds to the C-scan. And the C-scan is where the money is. That's why you need 3D. If you now scan with this technique, you can use multiple planes through the blood vessel. All you have to do is cut the vessel with multiple surfaces. So since this is volume flow, if there's no branches coming off, blood is conserved, so you can make multiple measurements. So you can get very robust statistics by scanning the flux across a whole bunch of different surfaces going through the blood vessel. Okay, this is a flow phantom. I'm sure many of you have seen this sort of thing. This is a standard 2D image produced by a 1D array, which one would see if scanning along the tube. So this is flow along the tube, and this would be very similar to what you would see if you were doing a standard color Doppler volume flow estimate. However, when you swing the array across, you get other planes. So if you're swinging the array across the tube in the axial elevational direction, you get this. This would be equivalent to rotating the probe 90 degrees. So this would be a very standard picture, and this doesn't provide the information you want. What you want is this, which is the lateral elevational slice, also known as a C-scan, where you produce this image, and every one of these images, every one of these pixels represents a Doppler shift that's perpendicular to the transducer face. So all you have to do is add these up. You don't have to angle correct them or anything, and that's volume flow. So the C-scan is where the money is. This is a picture of this. This is a standard, this is the C-scan from transverse image, and this would be what you would see in a longitudinal image. We want the plane that corresponds to this slice coming in and out of that section. And this is what you get. You get this sort of closed surface that's actually a torus, but it doesn't matter if you want to consider it a plane, where you just add up all of these velocity elements, and that's volume flow. Okay, well, what kind of consistency can you get? Here's a flow tube where we ran the pump at up to 20 milliliters a second. That's 1,200 milliliters a minute, quite respectable. The zeros correspond to the transducer being parallel to the tube. The X's correspond to the transducer or the aperture being perpendicular to the tube. Remember, it doesn't matter at all. And you can see these estimates are really good. Up to this highest estimate, the problem with this one was that the flow was going through so fast it was causing the pump to cavitate. So we were getting gas bubbles, which skewed the measurement estimate. But up to that point, this gave very good measurements in this setting. It also works for pulsatile flow. That was constant flow. In this case, the pump is programmed like a carotid artery, and here the pump is programmed like a femoral artery. And you'll notice that there's forward flow and reverse flow. It's triphasic, just like a typical femoral arterial flow. That doesn't matter at all with this technique. What you see here is something I'm sure you're not used to seeing. This is the original image, which is a transverse. By sweeping along the transverse plane, you get this image, which is now a series of high velocity, low velocity, and no velocity positions throughout the tube. The reason that that's happening is the pump is pulsatile, but the sweep is slower than the pump rate. So what we're seeing is the periodic flow in the tube. And in the C-scan, which is what we're interested in, this has exactly the same property. You can see there's high velocities and zeros and lower velocities. This doesn't matter if you want to measure average flow. And that's frankly what almost all the techniques that exist today measure. And what you do is you use something called the law of large numbers to compensate for this pulsatility, and you get a very good estimate of the mean. I'll show you that in a minute. Here's the flow in the simulated femoral artery. You notice in this one particular cross-section there's no flow, because remember the flow is crossing zero several times. In the longitudinal scan you can see it's forward and backwards, blue represented by the red and blue, and zeros all the way down the blood vessel. And in the C-scan there's red and zero and blue. None of this matters. It all works fine as long as you can sample long enough. That's the problem with pulsatile flow. So here's the law of large numbers. Here's a flow at 190 milliliters a minute. And you can see as you take more and more samples, as the number of volumes, you can get arbitrarily close to that measurement. We all know that this works. If this didn't work, casinos would be out of business. So this, frankly, works perfectly fine. The trouble is you have to sample a lot. Now this is a characteristic of the fact that we were using a mechanical scanner. If we could have done this with a 2D array, which is what's going to happen in the future, this kind of large number sampling will certainly be diminished. And you can see what happens as you do more and more samples, how the error falls off. And this falls off as 1 over root n, which is exactly what you would expect in this kind of circumstance. And you can get arbitrarily close estimates to the correct value. You can see that at 15 estimates, we're at plus or minus 5%, standard error of the mean. But like I said, all of this is occurring because we have a mechanical scan head. If we had a real 2D array and could do real-time 3D, 4D, 3D and 4D, this would not be nearly as big an issue. Okay, so here's a pulsatile phantom. And you can see there's the femoral, and there's a carotid, and you can see they estimate the true values very closely. And you can do different heart rates, and you can use different tube sizes. And remember, it's angle independent. So this measure is the correct match, and the reason we did this way is we have two different flow rates on here, 5 millimeters a second and 10 millimeters a second. So the perfect match would be 1, and you can see that the distribution is well within 10%, or very close to 10% in the upper limit, of an error for the correct value, independent of the flow velocity. What you'll notice, however, is that there is a wall filter range in which you can't detect Doppler. And clearly that occurs, this is a Doppler technique, so if you're absolutely perpendicular to the flow, you can't see flow. So this measurement will not alleviate that problem, so there's a dead area in the middle, just like there is with any Doppler technique. But as long as you can measure Doppler, this thing works really well. We've also done it, like I said, in dogs. This is the femoral artery. You can see there's reverse flow and diastole. It's triphasic. We then put a ligature around it, and you can see the classic pulsus tardus parvis effect. The diastolic flow is now above the baseline continuously. However, if you do the volume flow, even though the waveform is different, these are identical, basically. So there's no difference in the volume flow, even though the waveform has changed. If you continue to tighten the ligature, you can see that the volume flow, the waveform has gotten smaller, and the volume flow indeed does go down. So we now plot these different flows as a function of a flow meter measurement where we had a flow meter on the artery of interest. So we had gold standard measurements of all of these. These lines are plus or minus 15%, and you can see that these measurements are really tight around the correct measurement. The R squared was 0.95, and if you force the line through 0, the R squared is still a very respectable 0.93. If you distribute the error, you get a mean error of minus 7%. However, this is still unbiased because the standard deviation is plus or minus 9%. The full width at half maximum is plus or minus 13%. So this is a very good estimate. The other thing that's important to know is the flow meter itself, which we had on the artery, has a plus or minus 5% error. So this is a very respectable measurement of volume flow. So in conclusion, this can be done with mechanical or real-time 2D arrays. It eliminates the current limitations. It does very well when compared to gold standards, and I think this should be ready for prime time. And I would think that in the very near future, you're going to be seeing volume flow as one of the main applications for 3D scanners.